Hello guys, welcome back to my channel. And in this video I'm going to do another fun interesting integral. So let's get to it. I hope you enjoy yourself a lot. So as always, let's start with describing what the problem is. So let's call it I, and the problem is the integral from 0 to 1 of the natural log of 1 plus x squared divided by 1 plus x dx. Now at this point, if you want to pause the video and try this one for yourself, you can, and say if you're not convinced or you're not able to figure it out, then you can resume the video. Okay, I assume by this time you've done the needful, and although you may notice that the denominator 1 plus x could in theory be rewritten as a geometric series, because again we are on the interval from 0 to 1, so we are in the radius of convergence when it comes to geometric series. But that's not going to help, at least for this integral. It This technique worked for, I think, the last integral, but it's not going to work for this integral. And I'll tell you what's going to work. You can try other techniques too. You can try substitution, you can try Laplace transform, anything. But only technique that's what I believe is most reliable is Leibniz rule or Feynman technique. So I assume you know what the Leibniz rule talks about if you've seen my previous videos. So to apply Leibniz rule, you first need to find a suitable parameterization. Basically, you're generalizing the question, this generalizing integral I. And then after finding the parameterization, then take the partial derivative with respect to the parameter. And then you'll get some I prime of t or whatever. But since you want I back again, you want original parameter function back again, you reintegrate again with respect to the parameter variable from respectable upper and lower bounds, such that you revert back to I. And don't worry if you don't know what I'm talking about at this point. Don't worry, I'm going to explain as much as I can. So let's get started with the first step, which is parameterization. See you on the next page. Okay, so let me just quickly write what I was. It was the integral from 0 to 1 of the natural log of 1 plus x squared divided by 1 plus x dx. And one intuition, or I don't know, an observation after practicing the Leibniz rule many times is, if you have a natural log, then parameterize inside the natural log. Don't introduce another exponential term with the parameter. It's wisest to introduce a parameter such that we have 1 plus t times x squared. So hug the original variable of integration x with the parameter inside the natural log, and that works wonders. That's a general observation, because now you'll see why. So if we have I prime of t, this is just integral from 0 to 1, and then applying Leibniz rule of differentiating under the integral sign, we have partial derivative with respect to t of the natural log of 1 plus tx squared divided by 1 plus x and the dx. And now we have a 1 plus x in the denominator as it is, because that was a constant with respect to t, and now we have to apply the chain rule for the natural log. So we have 1 plus tx squared times the derivative of the argument, which is 1 plus tx squared, which is going to be just x squared, because 1 goes to 0. X squared is a constant, it comes out of the differentiation with respect to t, and then derivative of t is 1. So we just left with x squared and a dx. Fair enough. But we can still simplify this further, because notice we have a product of factors in the denominator. So this calls for partial fraction decomposition. Whenever we have a product in the denominator and you want to express this as a sum of two different partial fractions, partial fraction decomposition is the ultimate answer you have. So forget the integral for now. You have x squared over 1 plus x times 1 plus tx squared. You want to express this as something over 1 plus x plus something over the second factor, which is 1 plus tx squared. And since we have a linear term, we always need to have a polynomial of degree less than the denominator. So if you have a linear, we need a polynomial of degree 0 or a constant. Let's call that c. And here we have a quadratic of uh, degree 2. So we need a linear of degree 1. Let's call that ax plus b. And when you take the LCM and everything, you can cancel out the denominators on both sides. You have x squared equals x squared, grouping like terms, a plus ct plus x times a plus b plus b plus c. So comparing like terms on both sides, notice that there is no x term on the left hand side. So this means our a plus b that we had, a plus b must equal 0. And also we had no constant term. So that means b plus c should also equal 0. So this means a equals negative b and b equals negative c. So this means a equals c, and when we plug that over here, we have c plus ct, right? Because we have an x squared term, so this means a plus ct equals 1. So when you plug a equals c here, we have c plus ct equals 1. Factorize the c, 1 plus t equals 1. Divide by 1 plus t because it's a constant with respect to our original variable of integration, which was x. So we have 1 over 1 plus t for c, and since a is also equal to c, a and c both equal 1 over 1 plus t, and b is just the negative of that, so negative 1 over 1 plus t. Fine, we found our numeric coefficients for this partial fraction decomposition. Now all that's left is integrating both sides from 0 to 1 with respect to x. So what I'm going to do is I'm going to clear the mess above, and we know all these values. We just plug this up once I've cleared the mess. So once we know what a, b, c are, we can write our original integral, which was I prime of t, as basically the sum of these two integrals. So a is 1 over 1 plus t, b is negative 1 over 1 plus t. Let's factorize the 1 over 1 plus t factor out, and we just have the integral from 0 to 1 of 1x, which is just x, minus 1. So x minus 1 divided by 1 plus tx squared dx, and c is again 1 over 1 plus t times integral from 0 to 1 of 1 over 1 plus x dx. Okay, so how can we do this? We can further split the first integral into two separate integrals. So and I would also like to pull out the t from the denominator. So we have 1 over t times 1 plus t times the integral from 0 to 1 of x divided by 1 over t now plus x squared dx minus 1 over t times 1 plus t times the integral from 0 to 1 of dx divided by, we have x squared plus 1 over t, and we have 1 over 1 plus t times the integral from 0 to 1 of 1 dx over 1 plus x. Fair enough. Now, why was it that we broke this up? That's because notice that the derivative of the denominator is on the top, except we don't have the factor of 2, so we can introduce that. No problem with multiplying and dividing numbers, right? So we multiplied and divided by 2 to obtain that factor of 2 on top. And this is a classic form of natural log of the denominator, because if you have the derivative of the denominator present on top divided by the denominator, you have the natural log of absolute value of the denominator, which is x squared plus 1 over t. But since it's a definite integral, we need to evaluate that from 0 to 1. And don't forget all the constants that were present on this side. So we had 1 over 2 times t times 1 plus t. Okay, so we basically have this expression minus, I can write this as 1 over t times 1 plus t, and the integral from 0 to 1 of a dx over x squared, and instead of t I can write this as 1 over square root of t, but the whole thing squared. And integrating this is really easy. It's 1 plus t times the natural log of 1 plus x evaluated from 0 to 1, since it's a linear term and the coefficient of x is 1, so we don't even need to divide by anything. This is just the natural log of 1 plus x. Okay, so plugging in the upper and lower bounds, we have 1 over 2t times 1 plus t, and the natural log of, well, when x is 1, we have 1 plus 1 over t, minus when x is 0, we have natural log of 1 over t, minus 1 over t times 1 plus t, and this is a classic form of the inverse tangent. So this is going to be the inverse tangent of, we also need to actually multiply by this factor. This is a t. We have an inverse tangent of square root of t times x evaluated from 0 to 1 plus 1 over 1 plus t times the natural log of 1 plus 1, which is 2, minus the natural log of 1 plus 0, which is 1. So now I can write this as 1 over t times 1 plus t, and then I can express this as a difference of, this difference of log can be written as the ratio of arguments. So this becomes 1 plus 1 over t divided by 1 over t. Okay, so we have this natural log expression over here, and then we have a square root of t and a t, so one of those t's will cancel out, so we have 1 over, so one of these t's will cancel out, so we have 1 over square root of t times 1 plus t, and when I plug in 1, I have the inverse tangent of square root t minus inverse tangent when x is 0, we just have a 0 inside. And we just have this expression. So notice that the natural log of 1 is 0. So we have 1 over 1 plus t times the natural log of 2. And over here, if we take a common denominator, the t's will cancel out. We have 1 over 2t times 1 plus t times the natural log of 1 plus t minus 1 over square root t times 1 plus t, and in the numerator inverse tangent of 0 is 0, so that goes away. We have inverse tangent of square root of t plus 1 over 1 plus t times the natural log of 2, and that entirely is what our I prime of t is equal to. So we successfully found the partial derivative with respect to the parameter t. Now it's time to go on and get back our t by integrating with respect to t. So I have written down what I of t and I prime of t is. Now I would like to integrate from 0 to 1 with respect to t. And you'll see in a bit how that's helpful. So integral from 0 to 1 with respect to t. Because over here by the fundamental theorem of calculus we are going to have I of t evaluated from 0 to 1, which will just be I of when t equals 1 minus I of when t equals 0. So notice that I of 1 is when this parameter becomes 1, so we have natural log of 1 plus x squared divided by 1 plus x, which is nothing but our original question I. And I of 0, when you do that, we have 1 plus 0, which is 1 inside the natural log. So natural log of 1 is 0. So entirely this integral will go to 0 at when t equals 0. So this integral from 0 to 1 of I prime of t dt is nothing but I. So we got I, we came back to I in terms of other things, and simpler integrals that we can calculate on the right hand side. Okay, fair enough. So we know that this integral on the left is just I, our original problem. And well, look at this first integral over here. It looks like we can again perform partial fraction decomposition because the denominator is a product of t times 1 plus t. So this partial fraction decomposition, however, is very easy. This is just half of the integral from 0 to 1 of, in the numerator we just have a natural log of 1 plus t that will remain the same, divided by the first factor t dt minus half of the integral from 0 to 1 of natural log of t plus 1 divided by t plus 1 dt minus on the second integral. Why not make a substitution, because we have a square root of t many places. So let u equals square root of t such that du is nothing but 1 over 2 times square root of t dt. So this just becomes, and the upper and lower bounds remain the same. That's a great thing. Integral from 0 to 1 of inverse tangent of u divided by square root of t is u, 1 plus t is 1 plus u squared, and for the dt factor, dt is just 2u du. So 2u du over here. The great part is the u's will cancel out and we'll have a nice expression. Plus natural log of 2 is a constant which can be taken out, and the integral from 0 to 1 of dt over 1 plus t. Now I would like to use the Taylor series for the natural log here, because that's the only place we have a great job of actually cancelling out the denominator. So we have half of the sum from k equals 1 to infinity of minus 1 to the k plus 1 divided by k times the integral from 0 to 1 of t to the k divided by t dt And if you want to do a u substitution for we already took u, so you can take probably a v or something, p plus 1, so and a dv equals dt, but the upper and lower bounds now shift by 1, so we've integral from 1 to 2 of natural log of v divided by v dv minus 2 times integral from 0 to 1 of inverse tangent of u divided by 1 plus u squared du. This is just easy. This is natural log of 2 times natural log of 1 plus t evaluated from t equals 0 to t equals 1, like we had for our partial derivative part. So notice this becomes half of the integral from of the sum from k equals 1 to infinity of minus 1 to the k plus 1 divided by k times integral from 0 to 1 of t to the k minus 1 dt. And notice that if you want to do another substitution, you can go ahead and do that. But notice that we have a variable which is natural log of something times the derivative of of that variable, which is dv over v. The derivative of the natural log is 1 over v. So this will just become, this is just like u du if you want to change variables in your mind. It's like the integral from u du, which will just become half u squared, and in our case u is just natural log, so half natural log squared of v evaluated from 2 to 1. And then same thing over here, say our variable now is w and we have the derivative of w dw present, so this will just become half of the variable w squared, which is in our case is inverse tangent of u, but the whole thing squared evaluated from 0 to 1. And this over here will just be natural log of 2 times the natural log of 2 minus natural log of 1. So this, if you want to integrate, will be half of sum from k equals 1 to infinity, and then using the power rule on this, we have minus 1 to the k plus 1 divided by k, and then another k because of the power rule will make it a k squared and tk evaluated from 0 to 1 minus, over here we have half of natural log squared of 2 minus natural log squared of 1 minus inverse tangent of 1 basically squared minus inverse tangent of 0 but the whole thing squared, and natural log of 1 is 0, so this goes to 0. This becomes natural log of 2 times natural log of 2, which is natural log squared of 2, and here we have, well, we have 1 to the k, which is 1, minus 0 to the k, which is 0, so 1 times this thing, which is sum from k equals 1 to infinity of minus 1 to the k plus 1 divided by k squared times 1, which we can ignore. The natural log of 1 is 0 and natural log squared of 1 will also be 0 minus half of my apologies, there was actually a factor of 1 over 2 here, so 1 over 2 times another 1 over 2 by the power rule will make it a 1 over 4 everywhere, so 1 over 4 times the natural log squared of 2, and then inverse tangent of 0 squared again is also 0, and we have minus inverse tangent of 1 is basically pi over 4 but the whole thing squared, and we just have a simple natural log squared of 2 on this side. And notice what this is nothing but the Dirichlet eta of 2. So we have an alternating power, and k, the summing variable, is raised to the second power in the denominator. So this is nothing but the Dirichlet eta function of 2 because k is raised to the second power. And we have minus 1/4 of natural log squared plus this natural log squared. So we will have 3 over 4, 1 minus 1/4 is 3 over 4 natural log squared of 2 minus pi over 4, the whole thing squared, is nothing but pi squared over 4 squared, which is going to be 16. And now the Dirichlet eta of 2 has a special value of pi squared over 12 and minus pi squared over 16 plus 3 over 4 times natural log squared of 2. And this, on simplification now, taking common denominators and LCMs and stuff, is just going to be, we can write the positive term first, 3 over 4 times natural log squared of 2, and this is nothing but negative pi squared over 48. And all of this is basically equal to our I. We showed that for the left hand side. So isn't that fascinating? Another factor of pi just drops in even though we have a natural log and no trigonometric terms. Although, yeah, we don't have any trigonometric terms, we still have a factor of pi. So that's a really fascinating, elegant, nice result. Okay, so finally, in conclusion, we had our I, which was defined as integral from 0 to 1 of natural log of 1 plus x squared divided by 1 plus x dx. We used Leibniz rule basically, and then followed all the steps. We got three different integral expressions, four different integrals basically, which all of them we simplified, reintegrated. In some places even used the Dirichlet eta function, and finally we got the nice answer of 3/4 of natural log squared of 2 minus pi squared over 48, which is approximately 0.154723, and it has, I think, two more zeros ahead. So that's what this approximates to. So I really hope you enjoyed this video, guys. That's it for today. So please like, share and subscribe to my channel. You can follow me on Instagram. I post math art made on graphing calculators. Please recommend me to your mathophile friends, mathematicians, anybody you know. I just want to grow as a YouTube creator. That will help me make more of these interesting videos in the future. So stay home, stay safe, have a great day. Peace out.